Ja, då är det dags för Erik Nilsson.
So as the title says here, I'm going to be talking about machine learning today. I'm going to give a brief introduction about what I see machine learning as. Give a few classifications of what type of machine learning there is. And then I'm going to go straight to analyzing a data set of house prices and predict basically the sales price. So I'm going to start with giving you this nice picture of, it's a Venn diagram. The blue circle is artificial intelligence, which is a very broad concept. It's not very well defined, but it kind of means any computer software, something that acts intelligently, right? Machine learning is a subset of this, where you use data to train the computer software to do something, hopefully something it can do better with the data. So a lot of the artificial intelligence tasks are within machine learning, but not everything. You have a lot of stuff out here in the blue as well. And when you dig into machine learning as well, you have something called deep learning, which is typically what you use for speech recognition, image recognition. That's what you have on your iPhone when you get that face identification when you unlock the screen. I won't go there today. So I'm going to stay in the green zone. So there are basically two types of machine learning. You have one thing called supervised learning. What that means is that not only do you have observations of data, you also have some type of output. So it could be a classification of an image, as in having a cat or not a cat in it. Or it could be, as in this case, I'll show you later, house prices. You also have unsupervised learning, where you don't really have an output like that, but you use it more to draw some conclusions from the data. You use it in marketing, for instance, market segmentation. You have customer data, and you use unsupervised learning to kind of find distinct groups of customers. Use it a lot in social science research, factor analysis. I'll be doing supervised learning today. Here you have two types of problems that you solve. You solve regression problems where the output is continuous. So it's a number between a range, or it can be an infinite range. And you also have classification, where you have some type of binary output, or you have some type of category that you're trying to predict. So the first one is, you have weather forecast, for instance, stock market prices, and so on. On the second one, you typically have spam filter. Either it's a spam, it's not a spam. Simple as that. Image classifications can sometimes have thousands and thousands of labels. Still classification, although the numbers are a lot bigger. So that was kind of the background when it comes to machine learning and AI. So what I'm going to do now is show you a quick example of how you can use R to load data, clean data, and kind of the process behind how you do machine learning. So it's a slight focus on the algorithm, but it's more about how you actually test things, how you draw conclusions, how you set up the whole structure around it, so you can create a model that actually works. So the data I'll be using, or the problem I'll be solving, is a data set with 1,460 observations of sold houses over the course of 3 years. Each of these observations has 80 variables. Not all are present for each observation, and it is things like the size of the first floor, second floor, third floor. Is there a garage? Is the garage habitable? How big is the yard? Which neighborhood is it? There's a lot of variables, and they're all different. Some of them are representing an area, such as square feet of the first floor or the lot area. Some are categorical, such as which neighborhood, and some are categorical with some type of ranking in it. So it would be the quality of the pool, for instance, for those houses that have a pool. And basically the task here is within predictive analytics. So you basically, the end problem you want to solve is, giving this new advertisement or some random house on the street, what would the price be today? That's kind of what you're trying to solve. And in the intermediate, you use this data set of historical prices to kind of fit the model. So the process that I'm using, 4 steps. First, you take the data as it is, do some preparations, do some cleaning, and so on. Then you do feature engineering, which is basically sometimes the variables are in the wrong scale. Maybe you want to transform them using some functions, such as maybe logarithm or the square of the value, or something like that. You can also play around a little bit with the output. Do you want to look at prices, or do you want to look at like percentage difference between the predicted price and the actual price, or dollar difference, or how do you want to structure it? Model tuning, which is basically you start out with a couple of algorithms that you use, and all these algorithms have different parameters, and there's like an infinite amount of parameters you can use. Which one fits best? And the final step is, once you have a couple of candidates, which one do you select? And one thing that's probably worth to keep in mind is that, like usually like more classic statistics like frequency statistics and so on, the process itself is not that good when you do repeated trials. It's not really made for that. Whereas in machine learning, you want to be agile. You want to like come up with new ideas and try them again, and you make these improvements constantly. So you have to have like a process that makes that possible, if you know what I mean. I'm going to explain real quick what I'm using to get this done. It's not a lot, just 4 packages. They have dependencies, of course. I use data table in R, which is a table-like data structure. It's columns, each column 1 class. Every column, same length. Simple as that. ggplot is just this amazing tool for creating charts. Caret, that's what I'll be using for like the modeling, for structuring the process, right? And then you have xgboost, which is one of the algorithms that you use within this process. So by algorithm, I mean like linear regression would be one algorithm, and you're probably all familiar with that. And then to put the presentation and everything together, I use RMarked and IOSlice, and I might do some tweaking, but the idea is to put everything up on GitHub in case someone wants to like run through the examples and so on. Yeah, so first step, data preparation. Maybe the first thing you start with is splitting the data. You want to have save some data for after you've done your analysis, so you can have a clean data set that you haven't seen, you haven't touched, so you can figure out whether or not your model that seemed to be working very well on these 70% that it has been training on actually performs out of sample. So it's very important to take those 30% and put them away somewhere. And once you're done with everything, you can pull it back out and basically draw the conclusion on whether or not you're overfitting. The data I have here is kind of different. It's from a webpage called kaggle.com. They host data science competitions and have a shitload of data that you can just download and try these things out with. It's actually, I would urge all of you who are interested in this to go check it out. They do a 50-50 split. It doesn't really matter too much. And then one other thing is, it's important to like, if you want to visualize and you want to like do things that are outside of the machine learning process, don't use all the data, because if you use all the data, then you're going to make inferences, you're going to draw conclusions on the sample, and then you're going to test your hypothesis on the same sample that you just put out in the charts, and every statistical test, whatever you're making, is going to be flawed. So you just take maybe 10% of the data, make some charts, whatever, so you can see like general structures, get some ideas, and so on. Here's just printed out all the data there is. Like, these are all the features. There's a lot. I tried to like put together some nice charts, but I mean, it's a lot. It's a lot. It takes a long time. This is like one example of what it would look like. You have the ID, the subclass, which is some type of classification, residential, non-residential, and a lot of that. So it's a mix, numbers, characters, so on, so on. You also need to clean the data. Sometimes things are misspelled, sometimes numbers are wrong. You can't have a year that's 2020. It was something in like 2208. It doesn't really make sense. Some things are misspelled. You also have to create a strategy for handling missing values. Like sometimes a value being missing is significant, right? It could mean that, for instance, if the value for the pool size is missing, it means that there probably is no pool. Sometimes it's just because the data, no one put the data down, so it could be truly missing. It could be just random. There might be a pool, there might not be a pool. You don't know. So you have to, kind of think a little bit about it. In this case, there was a data specification file with the data that said kind of everything that was supposed to be in it, and whatever was not, you can just treat separately. So feature engineering, I'm not going to do too much here, but I'm going to explain the process. So you probably heard the word before. Basically, two types of things you can do here. You can use the existing values, transform them. It kind of depends on the algorithm you're using, but if you use a linear model, then you kind of want the relationship between the output and the feature to be linear. If it's not linear, you might have to do some type of transformation, use a logarithmic function or something like that. You can also come up with new features. Either you combine existing ones and create like some, let's say you don't have the area of the house, but you have like the height, the 2 dimensions, you can multiply them and get the area. That would be a very simple case. But it could also mean that you add data from other data sets. Like here you might have some location data, and with the location data you can figure so many other things out. You can know if there's like a good schools nearby or other things that could like improve the price or make the price lower. At the end of the day, what we're doing is some type of optimization. So we have to create some measure of performance. Typically you flip it and you talk about costs here. So the cost we're using in this case is the RMSE, the root mean square error of the log price. So it's the formula over there. Basically, the reason why I use log prices like this is because they represent like the ratio of change, right? So it's not, if you misclassify a cheap house by $1 million, that's a lot. But if you misclassify like a $10 million, $20 million house by $1 million, it's not that bad. It's not that bad. This takes care of that and just looks at the ratio. There's also some other symmetries in there that kind of makes it neat. So yeah, I'm not going to do too much, but basically the y hat, that's typical denomination for what you're predicting. So if you see the hat in machine learning, that's the thing you created from your model, whereas the y without the hat, that's the actual observation. Okay, so one thing you do with the model tuning, which is the next step, is that's kind of where you set the structure of how you, the idea is that basically you should be able to put any algorithm, very different algorithms, and compare them somehow. So you need kind of to step back a little bit and think about how do we test something that's more of a black box, right? Because some of these algorithms are complicated, some are simple, and if you want to compare the two against each other, you kind of need some type of different way of doing it. So what you do is cross-validation. You take your data set, randomly split it into usually 10 different sets. The first round, you take the first data set, put it away, use the remaining 9, train your model, and then you take and make prediction based on this model on the remaining, on the first data set that you put away, right? So basically you train your model on some data, you're predicting some other data, right? So you get like a measure of how good the prediction is. And then you repeat this for every data set. I can show you like a picture here, how we start with the blue one, and then you move the blue one. So the blue one will be the one that you make the predictions on, and the white ones are the ones that you use, like fit your model, basically. And when you're done with this, you just average it out, and you can redo it again. You can use sample randomly, do it again, and you do that a couple of times, and you get slightly better measure, but it's going to take a lot longer time to compute. So there's some, you have to strike a balance. What I do here when I create the model is I use, this is a function in the caret package, the train control. You use the repeated CV, repeated cross-validation method, 10 number of folds, so you split the data into 10 different sets, and you repeat the whole process 3 times. So you just create this object once, and then you use it again every time you train a new model. And that way you can, you have like one process for for everything. Okay, this looks a bit weird. Okay, let's skip this one. So usually when you do this, you want to have like some type of simple baseline model, right? You want to have like an idea about what's good and what's not good. Because what happens when you start adding advanced models and when you start repeating and repeating all over again is that you risk overfitting on your data. What I mean by that is basically, I mean, if you try enough random variables that don't have any information, and you do that like thousands of times, it's not that difficult on the computers these days. Eventually you're going to have something that just happens to align with the output variable. And you just magically, by being lucky, you're going to get some good results, right? And that happens in every step. Maybe the impact won't be that big, but there's always going to be some impact from it. So it's important to have like, start with some simple model and see how big of an improvement from a simple model that you know don't really overfit that much. And if you can't make a big improvement over that, you know, don't even bother with the fancy models. So what I do here is I specify the form parameter here. It's basically a formula. And on the left-hand side is what you're trying to predict. So the log of the sale price. On the right-hand side, you have the log of the first and second floors. All houses have only 2 floors. And then the neighborhood. Because like if you were to look at this data and I would just pick a few variables that would mean the most, like the size of the house and where it's located kind of makes the most sense to me at least. So I'm going to use this as the baseline. As data, the train data they have cleaned before, and TR control, that's the cross-validation object that I created earlier. So I'm going to reuse this for every type of model I'm using. The method LM, short for linear model, linear regression model. So everything you see here, like you use basically the same functions, typically use the same formula, slightly different sometimes maybe. You change the methods, sometimes you have some additional parameters you insert, but you kind of use the same tool regardless of what model you're using. And you can see here, this is what you print out afterwards. This is the important number, the cost function I showed before, 0.19. It kind of translates to plus minus 20% difference between the predicted price and the actual price. So it's, I mean, there's definitely some value to this, but it's not, I wouldn't say it's amazing. It's half decent. Yeah, exactly, it's better than the weather forecast. So next step, what I'm going to do here is I'm going to take some like much more advanced model, and that's capable of handling a lot of different like category variables, continuous variables, 80 different features as we have here. That's quite rare. It's not that obvious how to deal with it. So I'm using something called xgboost. So if you all know what like a regression tree is, this has nothing to do with the data, but the idea is still the same. So the regression tree is basically a set of like, it looks like a type of decision tree, right? So you start out with some variable. If it's lower or higher, you go left or right, and eventually when you come down to the bottom, you have a prediction. So models like this, they seem like very nice. They seem very intuitive. It seems like something you could just print out on a paper, and you can, you know, let humans use this model to make the predictions, right? The problem with them that as they are, like, they don't really work that well. The main problem is that they're very prone to overfitting. And you can see that because if you have enough depth in this tree, eventually you're going to come down to the level of the individual, right? The individual house, which means like, you know, if this house is on this street with this house number and this color, this is going to be the price. You know, that doesn't really generalize very well. So what you do instead, you have all these different hacks, different ways of making this model basically not overfitted data, because overfitting is the bad part. The good part though is that you can catch interactions. So you can have like, well, if this variable and also this variable, then we have this price. And that's very, very important. You don't really have that in a linear regression model before, because then everything is treated as independent of one another. You can also handle data that is not where there's not a linear relationship, but maybe there's like a U-curve or something like that. It might not be as good, but it can catch these things. So what you do here is, with the XGBoost model, you do something called boosting, which is you use, instead of using one model, you use like hundreds of bad models or weak models that are not overfitting, but they're also not saying that much. And the way you use it is, first you train one of them, and then you use the prediction error, and then you train the next one on this prediction error. And then there's like so many tweaks how to make this even better, and that's where the XGBoost package stands out, or the XGBoost algorithm stands out. It has all these like neat features, neat ways of like making these things work a lot better. So I'm going to show like how I specify the parameters I'm going to try out. So the way you do it is basically you have a range of parameters, and you create like all the combinations of these parameters that you can try out. So if this one varies between 1, 3, 5, and 10, and the other one 3, 5, 7, and so on, you test all combinations of the two, right? You don't have to do that, but typically it's a neat way of doing things. So I'm going to start from the beginning and explain real quick what they mean. So the first parameter here, the eta. What that one does is basically it takes the first model and then it multiplies it by the factor 0.05. So it makes it a lot smaller than it really is, right? So the impact of this model is going to be very small. N rounds is the parameter for how many of these models we're going to train. So here I range it between 250 and 2000. Typically the more the better. It's obviously related to how much we shrink each model. So the eta parameter, if that one is bigger, you don't have to do as many rounds. If the eta is a lot smaller, you have to do a lot more rounds. So the trade-off here is it takes a long time to train 2,000 models, or if you were to do 10,000 models, it takes a long time. So you kind of have to find a sweet spot. What you have here are 3 parameters that try to kind of make the regression tree a little bit less overfitting each time. So when I said before about like if you go deep enough, eventually you're going to reach down in this graph to an individual house. What you do with the first parameter here is that you say it can't be more than 3 steps. It can't be more than 5 steps. It can't be more than 7 steps. The gamma function is also another one which says that, well, if adding this next leaf in this tree doesn't improve the performance by this factor 1%, then we're not going to do it. We're not going to bother. And the last one, mean child weight, is basically we want to prevent it from having just one observation at the bottom of the tree. You want to say like, okay, if you end up with 1 observation, you don't bother. If you end up with 3, don't bother. If you end up with 5, don't bother, and so on. And the last 2 here is another kind of neat way of doing things. So in each of these potentially 2,000 models, this parameter is saying that we're only going to use 50% of the data randomly for each model, which means that every model is probably going to have different data to work on. That means that some observations that might be like have such a huge impact on everything else, well, they're only going to be in 50% of the samples. So you get like less dependence on these outliers, because it could be like some super expensive house that's really difficult to price, but it happens to, I don't know, something weird in the garage or something like that doesn't make any sense, but the model would pick up on it, and it would say that every house that has a garage like this is going to be, yeah. And the second one, call sample by tree, is to do the same thing, but you use the features instead. So you don't use every feature for all of these 2,000 models. And that also, I mean, it's difficult to really motivate exactly, it just works, but one of the reasons why it works is imagine if you had like 2 features that were exactly identical. Well, if you don't do this call sampling, then both of them would always appear at the same time, both of them, and it would be very difficult to like for the model to find out which one of them to use because they're identical. In practice, there's a lot of things that are almost identical, or they have a lot of collinearity between them. So by call sampling, you make sure that you actually separate these features, these columns in the data from one another in some of these training sets. So what I'm going to do next is show you how I run the model. Very similar to the before. I'm using the train function from the same package. The formula here, I replace the right-hand side with just a dot. That means like put in everything. The data is the same. TR control, same repeated cross-validation. So I'm using like the same setup as before. The tune grid, that's the one I showed you earlier with the set of parameters that you're going to try to look at. And then the method xgboost. So this like caret package, I think there's like 200 different models or something like that. Whenever someone makes a model, they typically try to fit it into this interface. So it can be used by people like me. So the way you figure out which one of these sets of parameters you want to use is you look at this RMSE of the log price, basically. You look at the cost function and see how low it can get. So on the x-axis here, or y-axis here, you have the cost function, and the lower the better. In each of these charts, the y-axis is the number of iterations. And we can see quite clearly that doing this 250 is not going to cut it. You have to like move out to maybe 1,000 or something like that. Then there doesn't seem to be a difference. So doing more than 1,000 doesn't seem to make any sense. And that's true for like all of these charts. What you also have here, there's no label, I realize, but the top here, 0.5751, I think that should be the call sample, the column sampling. There seems to be some difference. It seems to be that if you use this, if you put it to 1, then you're not using the feature at all. That's like negating that parameter. And they don't seem to be, the ones to the far right don't seem to be as good as the other ones, right? And it seems as if the most optimal value is found on 0.5. And here, vertically, 3, 5, and 7, you have the depth of the tree. So the higher up, the more weak these boosted learners are, and further down, the stronger they are. So the problem is like if you increase that number, you're probably going to overfit in your data. You're going to find things that just exist in this data set that don't really make any difference, make any sense outside of this data. They don't generalize well. So I'm not really surprised that this one comes out on top. So you see the one here with the black little square around it. That's the most optimal parameter, sets of parameters we can use. So this is a nice way of like visualizing it. And of course we can just put it into like an algorithm and optimize it and get some output that says use these parameters and so on. But it's not really that easy, and I think I'm actually making like a bit of a mistake by simplifying it like this, because there's a lot of randomness here as well. Just because this one happened to be the best here doesn't mean that the next time we run it, it's going to be the best, and so on. So you might also want to have some measure of like how certain is the RMSE for this set of parameters. And typically when you do this as well is that if you have like two sets of parameters that are very similar, you have to have some strategy for picking one over the other, and typically you try to choose the one that's the most conservative. That's the simplest. And the reason is to some extent because maybe you'll be able to interpret it better, but I would say like the big reason to choose a simpler model or a more advanced one is that typically it's not as easy to overfit a simple model as it is to overfit a very advanced one. So I think this value up here kind of I mean, it looks good. Well, it's quite conservative. You don't have to run 2,000 iterations. You can save computing power by just doing, I think, 750 as it is there. So it seems to be like a good set of parameters for this model. And the final step is comparing the two. So here I only have two models. You probably want to try some other types. There are different versions or like extensions of the regular linear regression we have here. You can do a lot of fun stuff there, and the point of using models that are like fundamentally different, such as a linear regression model and a tree-based model, is that they're able to capture, like they both have flaws, they have different flaws, so they will be able to capture different things, right? What we see here in the column train RMSE is that the XGB3 is a lot better. It's down to 0.12. So roughly translates to plus minus 12%. But I'm actually going to include another measure here at the far right, which is the mean average error. So instead of with the RMSE you square each value, here we don't take the absolute value. So it's when I say that the one to the right means plus minus the typical error is 8%, that's literally what it means, or almost literally what it means. Whereas when I say that the other one with the other measure it's plus minus 12%, that's not really true. And sometimes it's good to have different measures because they have different strengths and different weaknesses. The one in the middle, the one we've been using to train everything, if you have like a really big error, it's going to have a huge impact because we take the square of the error, right? Whereas in the other one, you don't take the square of it. So you're going to get slightly different output there. Yeah, that's it for me. Thanks for listening.